Now that we have some random cutter planes slicing through our geometry, let's start adding some interesting detail to this so that we can art direct it. We're going to start by adding a mountain noise, and you can also play around with using the attribute noise instead if you'd like. They're both slightly different ways of applying noise to the surface. In the case of the attribute noise, you would have to change the attribute that's receiving the noise to P, leave it on additive. I would check center noise on so that it gives you values from -1 to 1 instead of 0 to 1. And anytime that I'm working with three-dimensional noise attributes like this, I often copy the X position and then paste the relative reference into both Y and Z. So that way we can just change one value and have the other two match instead of just bouncing back and forth. So we could turn that amplitude up to 10. In this particular case, that element size is pretty tiny, so we'd have to go much larger with that. Maybe try something like 30 for this, with an amplitude of 20. And you can see we're starting to get some interesting results out of that attribute noise here. Alternatively, you could use the mountain noise as well. It's a very similar set of controls. If we match the same values, let's see, it was an element size of 30, give it a height of 20. And if we look at the two options, they're a bit different. They have some similar controls. They're both using simplex noise, and it's kind of personal preference, whichever you'd like to use. Now, in previous versions of this cutter generator tool, I've used mountain noise for both the low frequency and high frequency detail layers, but I'm going to try switching over to attribute noise, at least for the low frequency layer. Now, as we've seen, they are pretty similar, but I recently found out in testing some offset overrides that the attribute noise gives us some more flexibility than the mountain does. Now, this is really important when we start looking at some really big low frequency details. So let's increase our element size up to 200. We could even try higher if we want. Let's try 200 in the amplitude. Heck, let's even see what 300 looks like. So for the initial layer of noise, we want to get just really big, broad features that are, carving just interesting paths all through our geometry. In this particular case, I'm not really liking what all of the octave details are giving me. It makes it harder to see what's happening in there. It's not problematic by any means, but if we turn that down a little bit, then you can see those big broad curves a little bit more clearly. Now, if we find a spot on our cutter geometry where we have some nearly parallel planes, like this area here, you can see where the problem arises with these low frequency layers. Now you can see that these layers here are following a pretty similar shape. They're lining up with each other and flowing the same way. And these original planes before the noise probably were somewhat parallel to each other, something like that, and with a really large element size here. When you sample the position for each of these, then you're going to get pretty similar values at these nearby parallel positions. Now maybe in some cases you'd want your crack lines to kind of flow similarly like this, but we don't want that for our default cutter generator behavior. If you want some matching flow directions like that, you could set that up by hand, maybe hand place a few cutters and apply noise to them in a more manual way, but we want the default state of our randomly generated cutters to be much more random than this. Now, in previous versions of the cutter tool, where I was using the mountain noise, I would have to use a for each loop, which you can drop in like so. We'll talk a lot more about these for each loops throughout the class. In this case, I would drop in for each connected piece, which just creates a connectivity node for you. which will give you a class attribute with a different value for each one of the cutters based on whether they're a continuous connected mesh or not. And then in our for loop, this would run over each one of those individually, and then inside there, we could give each of those a different offset on the mountain noise. You can see if we view the mountain there, and we give it some really big offsets, we can vary the noise pattern that way. And then to vary this per piece, we would either have to create the metadata node for that for each loop, and then you can use the iteration detail attributes stored in there. We'll probably look some more at this later. Or you could potentially use the class attribute for each one of these pieces, since that's unique per piece. But that's a bit more of an annoying setup. And these for each loops are really useful, and we will use them a lot. But anytime that you can avoid using that and use a setup that doesn't require them, things will probably be running faster, and they probably will be easier to set up. So in this particular case, on the attribute noise, we can just drop in a wrangle node, and we can create an offset attribute that this noise will detect. Now, lots of Houdini SOPs will allow you to override the parameters on a per point or per primitive basis by looking for attributes that match the parameter name. You can get a hint as to what some of those attributes are by hovering over these parameter names. In this particular case, if we look at the offset, if we hover over that, you can see that this parameter name is offset X, offset Y, and offset Z. So if we go to our wrangle node, and let's display our attribute noise first, inside this wrangle, let's specify a vector that will match that. So we can say v at offset equals, and I'll use the curly brace syntax for the moment, we'll give it an offset of 1260 in Z. And if you hit Control Enter in your Vex window here, that will execute your change. If you just try to hit Enter, it'll just create new lines. So that Control Enter is handy for telling it to run your change without, needing to click away or anything. And you can see that this has given us an offset based on those numbers that we just entered in Vex there. Now, unfortunately, this doesn't seem to work in the mountain node. If we connect our offset wrangle to that, and of course, let's keep our scene clean by naming this cutter noise offsets. And if we view that mountain noise, you can see when you select that mountain noise and hover over the offset, this also says that the parameter is called offset X, Y, and Z. But if we bypass our wrangle and look at the mountain noise with and without that, you can see it really makes no difference. So this is one of those things where it's a nice feature that is built into many Houdini nodes, but it's not always available and doesn't always work where you would like it to. Now, because this does work nicely with our attribute noise, we'll just delete the mountain for now. We'll call our attribute noise low frequency, and then we just need to vary this per piece, because right now the parallel planes are all getting the same offset. You can see that these two parallel ones that we were looking at before are still getting some pretty similar flow and shape to those values. Now, to get a unique value per cutter that we can use to vary that offset, we can use that connectivity node that I pointed out a moment ago. If we just drop that in here, this will create a class attribute with a different value per cutter. And I think we created 10 cutters here. So if we look at the spreadsheet for that connectivity node, you'll see that it's creating an attribute on points. With the connectivity type, you can put it on prims instead if you'd like, which we will be using a lot later. And you can see we have, sure enough, 10 varying values, 0 through 9, for each of those cutters. Now, in the wrangle node, we can use that class value to create some sort of random offset per cutter plane. Now, if you pull up the Houdini help window and search for the Vex functions in here, This gives us a really helpful list of all the different vex functions that you have available. Although sometimes I like to look this up in a web browser instead, because sometimes I find that a little bit easier to navigate than Houdini's own help window. But in any case, we can search for the rand function. And if you select this regular rand function here, you can ignore all of the special versions for now. You can see that there are lots of different variations on the same random function. Sometimes you'll want just a random float, which is just a random decimal value. Sometimes you may want a random vector with, a different random value for all three x, y, and z dimensions, and so on and so forth. And you can see you have options to specify a vector seed or a random float seed, or etc. In this case, we want it to return a three-dimensional vector for our offset, and we just want to provide it one value for the seed, which will be that class that we computed with the connectivity node. Now you may be wondering how to specify which version of the rand function you want to use, but Houdini knows to figure that out based on your input. So here you can see we have a vector offset attribute that we're creating. So that means that it will look for the rand function that matches the data type that we're searching for. So let's minimize that help. We can type in rand based on I at class as the seed. Hit Control Enter, and sure enough we will get some random vectors for each one of our cutters. We can verify that by going to our spreadsheet and expanding that here. And if you scroll down, you should see your offsets are all the same for each value of that class. So just scroll down, and once we see that class change, sure enough, our random offsets do as well. But right now, this is only giving us offsets between 0 and 1. So we can vary this offset a whole lot more by adding a multiplier to it. I'm going to right-click the spreadsheet, tell it to always stay on top, and then in our offset here, I will just say 10,000 times whatever that random return vector is. Hit Control Enter, and sure enough, we get these really large offset vectors that vary between 0 and 10,000. Now that we have a lot of nice low frequency shapes on here, we can go in and start adding another layer of noise for more high frequency detail. Like I mentioned earlier, you can use attribute noise or a mountain. I'll just stick with a mountain for this one, because with the high frequency detail, we don't have to worry nearly as much about those big shapes lining up. So I'll just connect that mountain noise like so, and I'll add a lot to the height, make it like 20, maybe an element size of 20 as well. And now we're starting to get some really nice broken up shapes in here. If you zoom in closely where a lot of those cutters meet, you can see how all of these interesting cracks will create some pretty convincing concrete shapes once we use this to run a fracture. As an optional step, I often like to add a subdivide for some extra mesh resolution on that detail layer. Of course, you could just increase the resolution of your original grids, but that will slow down all of the previous processing, and as you'll see in the next video, we're going to trim off some of these unnecessary areas before we continue on with the fine layer of detail and some final processing on this.